Modern turbochargers are based on a simple principle. If the air entering an engine is pressurized and more oxygen forced in, then by adding more fuel, the result is higher engine torque and more power. At sea level, there are 0.016 pounds of oxygen per cubic foot. At higher altitudes, the air is thinner, so there is less oxygen available. For example, at 5,000 feet, there are 0.013 pounds per cubic feet, and at 15,000 feet, there are only 0.01 pounds per oxygen per cubic foot. So as altitude increases, it becomes more difficult for an engine to obtain the mass of oxygen it needs to generate its required power. In a naturally aspirated engine, the only force pushing air into the engine is the ever-decreasing atmospheric pressure. With less oxygen available for combustion, the fuel is only partially burned, and some escapes out of the exhaust as black smoke. A turbocharger helps to supply air by forcing it into the combustion chamber under pressure. It is able to do this since the reduced atmospheric pressure makes the turbo stage more efficient. Thus, the engine can maintain virtually the same air-fuel ratio as at sea level, with almost no change in either power output or exhaust emission levels. Turbocharger technology evolved from mechanically driven superchargers, which create boost pressure using a mechanical pump driven directly from the engine. However, the inefficient supercharger is an engine parasite. It uses a large portion of the potential power increases to drive itself. For example, a supercharger that could theoretically raise a 220 horsepower engine to 370 horsepower could only manage 320 horsepower. The supercharger itself absorbs 50 horsepower. Because a turbocharger is able to utilize both the pressure and heat energy of the engine exhaust gases without taking power from the engine, it is far more efficient.